Okay. We have several QR codes right here. If you are going to the tour that we arranged, the first one is TSMC, the semiconductor company. Second one is ITRI, the Industrial Institute. So if you are going to those, you need to make sure you scan the QR code and let us know you're going. I know many of you already complete those. If you didn't, you need to do it. For today's attendance, you can complete the left lower QR code. And if you are non-Taiwanese, for your trip, we need to have some of your personal information in order to provide insurance for the trip. So you need some information on the right-hand side. Okay, so for today, I'm going to share some of my previous research experience and kind of let you know what you can do for different kinds of research or topics. Because right now, you probably are still trying to find what's your future research direction. And I am a very multidisciplinary professor. What does multidisciplinary mean? It means when I work on the research, I don't only focus on one direction. I have worked on research topics in different directions. And for the presentations I'm going to show you today, very briefly and very simple explanation. I will show you some topics where I worked on in the past, and they are in the field of 4 departments: mechanical engineering, civil engineering, chemical engineering, and material science. I did a little research in every department, in every research direction. So I hope you can kind of have a broad glance of all kinds of research directions. Okay? So let me talk about mechanical engineering first, because I'm from mechanical. So it will be easy for me to talk more about mechanical. So Taiwan Tech is actually okay. Okay, I think I opened too many software. It's kind of weird right now. Hold on. My software is not responding. Let me open this one. Okay, I hope you're okay this time. I don't know why. It's happening again. Okay, I don't know why. Maybe the resolution. Let me lower the resolution. No? How about this? Okay. Okay, good. So, Taiwan Tech, in the past few years, okay, I'm back. I'm back. So in the past few years, there's a subject called Industry 4.0. It's a very advanced research or industrial development direction created by Germany. And all other manufacturing countries started to do something similar to Industry 4.0, including the most important countries such as USA, Japan, China, and some other countries in Europe. So Taiwan did similar things, but we didn't call our Industry 4.0 the exact same name. At the time, we called that kind of research direction as Productivity 4.0. Productivity 4.0, okay? But that name was created by previous president, the Taiwanese president. And this name came out not for long because there was an election and the other political party won the election. So we had a new president. And do you guys know about the non-Taiwanese students? Are you guys know about our political party in Taiwan? The blue color and red and the green color?
Yes.
You know the colors, right? What color are we in right now? Green. We're in green color era. Yeah, the president is from the green color party. Previously, we were in blue color. Yes, 国民党 and 民进党, yes. So, the Productivity 4.0 came from the blue party, the 国民党. The previous president, Mr. Ma Ying-jeou. And now we have the current president is President Tsai Ing-wen. She's from the Green Party, 民进党. And this kind of very important name for a very important direction usually will be created by our government. And since our government changed color, so the new president decided to reject the name of Productivity 4.0. And she used a different name. But they're the same thing. They're basically Industry 4.0, but we use a different name. So for right now, we usually call this as smart manufacturing or intelligent manufacturing. Okay? And at the moment, Taiwan Tech was one of the earliest university which started to build a factory, a smart factory, or a factory for intelligent manufacturing. And it's a research center. So in Taiwan Tech, we call it Industry 4.0 Center. So at the time, you can see we had so many companies and research organizations joining this opening. Okay, we are the very early university. We are the universities who started this Industry 4.0 very early. Okay, so I have been working on another educational center in Taiwan Tech in the same subject, in the same direction, intelligent manufacturing. And this is a platform that groups different departments and schools together. professors and graduate students and undergraduate students will learn how to do Industry 4.0 or smart manufacturing under this platform. Okay, so we are the leading university for this platform. Okay, and inside this platform we have departments from. We have departments from mechanical engineering, right here, ME. Turn on the pilot. No? That's a point. Okay. We have Department of Mechanical Engineering, Information Engineering, Material Science, and Control. Graduate Institute. And over here, this is another school. This is National Normal University. And this is a private university, Zhongyuan Christian University. So they have people from electrical engineering and industrial engineering, and some other schools. Okay, and we realize in this, nowadays, almost every engineering department needs to learn something about digital technology or technology related to internet. And that's usually some subject that will be introduced in the information or electronic or electrical department, not us. However, we are forced to learn things like that. All of you will need to learn something like that later on. Okay, because almost everything is in all kinds of direction. You will use some kind of equipment, and internet technology right now is so common. You may need to use something that linked to the internet, and use some intelligent applications to achieve some missions. So nowadays, students need to learn many different things, not just the subject in your department. Okay, so we create this crazy course map. This is not for one person to finish. It's not like a map that everyone needs to complete. If you are, for us, we are in engineering, so we use mechanical engineering as an example. Those are required courses for mechanical engineering. And over here, those are the courses from the Department of Computer Science or Information Engineering or EE, Electrical Engineering. And we found there are some overlapping courses. So we do learn something similar. We all learn the same subject, but we just don't know how to work with someone from the other side. So this map is for students and teachers to understand, okay, I'm from the engineering side. If I can learn something from computer science, probably I can do some advanced research. Those are more advanced research directions. Okay, so like my students, all of them needs to do programming. For traditionally, like 10 years ago, not all the mechanical engineering students needs to do programming. But nowadays, almost everyone needs to do it. Okay? So this is the trend. And I guess you have never heard of something like this. So this could be the first time for you to understand the architecture of Industry 4.0. So what does that mean? You don't need to worry about what's on the right-hand side. Let's take a look at the left-hand side. This is like a hierarchical structure indicating how this network is going to work together. So at the bottom, we call the sensing layer or machine layer, which means in a factory, like a chemical factory or mechanical factory, production factory, all kinds of factory. We usually have machines, all kinds of machines, and we usually have tons of sensors, like a thermocouple or all kinds of meters. And in the Industry 4.0 architecture, we would like to collect information from those machines and sensors. So over here at the middle, it's called the control layer. We usually collect those information in order to make proper decisions about control. We need to know how this machine operates. Okay? So once we have, those are like multiple devices, multiple machines, multiple sensors there at the bottom. And right over here, we call this edge layer. Edge, what is the edge? Why do we use the name edge? Because this is like in the physical world, something you can see. And this is at the border between the real world and the internet. So at the border, at the edge, like my cell phone. My cell phone is a device, it's a machine. It has a sensor inside. My finger touch could be detected. So there's a sensor inside, it's a machine. And this machine sends information to the internet. So at the border, there's you cannot see it, there's an edge layer. And there are people working on research for what needs to be done at the edge. How you can send information to the internet. Okay, at the border, what do you need to do? Okay, so once you send all kinds of information through the edge, going to the cloud. So sometimes people call the internet as a cloud. It's like on the sky. It's like internet is in the sky. So they call it a cloud. So once you are up there, you will do all kinds of calculations up there, such as you will be storing all kinds of data. For example, you are logging in Facebook, and your cell phone will keep your password or some personal information, or like whatever you're typing right now, or what your friend is doing on Facebook. If you're watching Facebook right now, then all kinds of data is in the internet, right? And that's why they call the data layer. But this kind of structure for manufacturing, we care more about how to manage. So on the top, there's a management layer. Okay, so under this structure, there will be professors who teach different courses in different areas of Industry 4.0 architecture. So every professor can only learn so little. For myself, probably I only know how to utilize sensors and machines to do some research, maybe do some control. But I cannot have good research background about how to do management on the internet. But for you guys have to know technology nowadays are built up like this. You can be taking courses everywhere under this kind of umbrella, under this kind of platform. And maybe in the future you can have better sense of how this structure works. if you can do something under the architecture of Industry 4.0, it will be very easy for you to find a job in the future. Or maybe when you go back to your own country, you get basic knowledge and skills about Industry 4.0, and probably your knowledge is more advanced than your friends or people with similar ages in your own country. So probably you can start your own business with those advanced technologies. Okay, so that would be what Taiwan Tech is doing, and next I would like to show something interesting to you, because I don't want you guys to feel bored. So for myself, in order to create the idea of humanless factory, for an intelligent factory or smart factory, we wish we don't need so many human workers inside the factory. Computers and robots know what to do, and they can do the work by themselves. So in my lab, I teach my students how to do research in the field of robotics. So let me show you a video of my student building a robot. Sorry, a lot of things in Chinese. Basically, this is about remote control. Like in the architecture of Industry 4.0, you may need to control something remotely instead of control on the site. So at the moment, this was done several years ago. At the moment, remote control for robots was not easy. And over here, we were trying to improve the accuracy of a robot. If I ask a robot to do something, but it's not accurate enough, it may make a mistake. So over here, we use some measurement tools. Those are some measurement tools. We try to measure what's the error of positioning. If I want the robot to tighten a screw, and there's a 1 millimeter inaccuracy, the robot may fail. So over here, we did some measurement and then apply algorithms to improve the quality. So those are just videos about how to improve it. From the video, sorry, I should. So from the video, you can see how a machinery factory looks like. There are all kinds of machines in the back. If you are going to take courses in mechanical engineering, eventually you may learn how to operate a cutting machine. So this is how a factory looks like. It looks a little bit dirty and a lot of huge machines, and it looks a little dangerous, but that's where the fun is. Okay? Anyway, so this part of the video is about integrating a camera with a robot. There's a camera right here on the top, and my student will be placing an object underneath the camera. And the camera will recognize the object and recognize a small circular hole on top of the object. And there is a cylindrical pin right here. The robot will grab the pin and insert into the hole. And the tolerance was very small. So if you cannot position the hole properly, you cannot assemble that cylinder into the hole. Okay, so let me show you the video. And if the robot can do this, then we don't need human workers to, do simple things like this. So the software just recognize the circular hole on top of the piece right here. And the robot is now grabbing the cylindrical pin and insert into the hole. Okay? And this position was randomly placed by the student. So if you need to place the object to the exact position, then that will require some extra work. But if the machine can identify the position by itself, then that saves a lot of time and it creates intelligence to the robot. Okay, and this is another video and another robot. This is a robot that was made by another group of students. Actually, another student, one student. He made this robot by himself. So this is for you to kind of get a feeling about how to make a robot. First, you model in software and test its movement. Because if you design a robot and it doesn't move properly, then you cannot continue. You need to make corrections. So from here you can tell he was able to move the robot arm freely to any place he wants. Okay? Then what he needs to do is to prepare the circuits. Inside all kinds of machine that is powered by electricity, there's always electronics, circuits, mechatronic systems inside the robot, inside the machine. And my student is building those little by little. So now this is a video about him trying to preparing the circuits inside the control system. And he purchased some of the devices. Those are called the drivers. Drivers are devices that tells the motor what to do. A motor is a machine that makes rotations. Once you provide electricity and some control command to the motor, it rotates based on your needs. But in order to communicate with the motor, you need something called driver. Driver understands how to control the motor. So now he's hooking up all the drivers. This is a power generator. It converts the electricity on the wall to the proper voltage for the system. Like those are for safety. And those are like connection parts for the wires. Okay? So once you're done with the driver, you hook up with the motor. Let me show you what the motors look like. Okay, those are motors, like a huge box, and there is a cylindrical part at the top. So when you put electricity in there and command, it will rotate. Okay. So he used a control system to give commands to the driver, and the driver gives commands to the motor, so the motor will be spinning based on his command. So you can see how the motors are spinning properly. So afterward, the work pieces has been manufactured. So what he needs to do next is to assemble it. So this is like a professional Lego toy. Okay, very expensive Lego toy. So if you do research in mechanical engineering, sometimes you build real machines like this. Okay, and this is one of the motors, the largest one. This motor is like the shoulder of the robot arm. And all the electronic circuits are inside the table. So if you feel fascinated about robots, then you definitely need to choose mechanical engineering. Okay, so at the end, you need to test whether all the motors can operate at the same time, so the robot can move as you wish. It's a pretty cool project. Can someone guess how much this robot cost? Let's have a fun activity. Can someone guess how much? Are you guys already familiar with Taiwanese dollars? Right, so let's guess in Taiwanese dollars. Is it $10,000? 30,000? Definitely not enough. Okay, an easier one first. How much is that table? Robot table, how much? 5? 10? 10,000?
It's made of metal, right?
It's made of metal, yes, very heavy. It's around 100 kilogram weight. It's very heavy because when the robot moves, it causes so many momentum. So you need a really heavy table. What's your guess? 10,000? 20,000?
More. 40,000.
40,000?
Only the table.
Only a table.
100.
100,000. 100,000, 10万. Only a table. Because it's made of metal. I pay for it. My research funding. Okay. Well, so how about the robot? It's even higher. Higher than the table. So it's 800. No, that's too high. It's around 300 or 400,000 for the robot. 30万 or 40万 in that range. If you have, let's say, if you have 300,000 Taiwanese dollar, you can buy a robot arm like this. If you have 300 or 400.
Yes.
So that's approximately 1 year's salary for of a young full-time worker in Taiwan. The year salary. So if you save money for your salary for the entire year, you can buy a robot arm.
How much per motor?
Say again?
How much per motor?
The motor? Motor is around less than 100,000. It's around like the big one. Big one is the most expensive one. Probably 70,000. 70,000 Taiwan dollars. Yeah, it's not cheap. Okay, like right now in my lab, we have a very huge robot arm. It cost me $1.5 million. 1.5 million. Those are governmental funding and industrial funding. So my student and all of my students and I work together on research topics, and we get funding for advanced research like this. Okay? So it looks like something that you probably cannot work on, but this one you can. So this is a course that I offered in the past. In this course, students will be integrating different technologies and very cheap and easy, simple technologies. So there's a camera on the top, outside of this view. With that camera, students will be making computer programs to identify the position of that yellow ball. And since the students know the position of the goal right here, so they were able to calculate where exactly the robot arm should be located and how much speed and what direction to move the robot in order to kick the yellow ball toward the goal. So from this example, you can see how image processing, cameras, and robots can work together for some interesting applications like this. So can you guys guess which year was the student right here? Freshman, sophomore, junior, or senior? So I offered the course and some student took it. Was he in freshman, sophomore?
I think he was freshman, yeah?
No.
He was second year?
Yes, sophomore year. So it was an elective course, and when they came to the course, they knew nothing about this. So how can they integrate technologies from different disciplines? Because we provide templates of all kinds of things, like image processing. We already complete some prototype for those applications. They can follow up what we build up, and they can easily learn the things that they need to learn. So those examples are for you to know. You will be seeing or taking all kinds of courses like this. In the subject, you may need to learn different things in different disciplines. And if the professor or the teaching group provides some prototype, you should be able to learn the subject quickly and even achieve very simple applications like this. But you won't be able to get to know the deepest skills inside the subject unless you spend time in that subject. So nowadays, for students, usually you will have many opportunities to take a look at all kinds of research, but they are only at the very like, how do I describe it? It's like it's at the boundary of the knowledge. You haven't go deep into the knowledge. So in undergraduate programs, you are exploring at the boundary of all kinds of different fields. And when you pick up a subject that interests you, you need to go deep, okay? So, another example right here, this is my graduate student. They had a 3D camera on the top. On the upper right corner, the 3D camera will recognize the surface of the item. That surface has a tilting plane, and the student places it randomly on top at the beginning of the conveyor. As the 3D scanner recognizes the surface, it will tell the robot arm what position this surface is and what's the orientation of it. So later on, the robot will move to the right position and wait for the object to slowly come closer until the camera has a aim of the object. It will follow the object in order to do live monitoring. So on the right, on this area, you can see what the camera sees. So over here, he reached. Did you see this view doesn't change as the robot moves because the robot is moving along with the object. So if you have this kind of automated system in a factory, you don't need to make stops. Because in production, if you make stops, that occupies some time. Time is money. So if you can save some time here and there, you can save some money. And that will reduce your cost, and then you can end up with earning money. Okay? So those are like a very brief introduction of some applications in the field of mechanical engineering. Next, I would like to talk more about, how about this one? This one is related to civil engineering. So in the past, I worked with some other professor in my department. We were working on UAV. So we were working on unmanned vehicles, like you guys know unmanned vehicles, right? And we placed cameras on top of UAVs, and we want to use it to do some applications such as inspections. And inspections could be useful for civil engineering, like bridges or architectures, buildings, and since the UAVs are able to fly high and far away and reach closer to the building, it's safer for human workers. If we need to climb up to inspect the bridge, it will be very dangerous and costly, and it's time inefficient. So nowadays, there are many companies or research centers, they developed how to use UAVs to do inspections. So there are like inspection needs for power plants, or this is like a checking. You can use it to detect pollutions, the air qualities, or inspect the building structures of a power plant or for wind turbines. So we have worked with some governmental institutions that is related to the wind turbines in Taiwan. And they told us, if you send a human worker to the top to inspect the wind turbine, it's gonna cost around $100,000 per inspection. 100,000. Yes, $100,000 per inspection. So if you can use a UAV to fly to the sky and take photos of the wind turbine and perform proper analysis, maybe you don't need to spend that much money. You can maybe reduce it to half. Okay? So like there are bridges this long. If you need to inspect the bridge, you may need to block the area. And since this architecture is so large, so long, that may require a long time, then you will affect the traffic for a long time. That's actually very high in the cost. And also, for inspections, sometimes human workers will stay on the like inspection truck like this. In Taiwan, they call this crabs. They call this crabs. The arm looks like a crab. They call this crab trucks, but in Chinese. There were incidents about trucks falling because of the imbalance or maybe unexpected events, and that could be costing someone's life. That's why previously we would like to do research on UAVs. And over here, this is another example about digital technology and internet. This is like internet of vehicles. We have control systems. We could be controlling flying vehicles, ground vehicles, helicopters, and on top of the vehicles, we can carry all kinds of sensors. So this is just another example of Industry 4.0. So I'm gonna show you some video that was taken by my colleague. So he was taking pictures of a building. This was a building in his research center. I think this is in Germany or Poland, because my colleague worked in Germany in the past. So he took so many pictures of the building, hundreds of pictures of the building, and then stitch them together. So this is like a complete inspection map of the entire building. Okay? So what happened was, if you zoom into this huge image, you can realize, okay, in some part of the building there were cracks, and we need to monitor the growth of the cracks and also do proper recovery to the building. Okay? And for the rest is about my research. I was working on some image processing technologies to identify the positions of the cracks. Like this picture, if you have good eyes, you may see there are vertical and horizontal cracks on the wall. This is true picture taken by a UAV. But with image processing, you can see those cracks even better. Like over here, there's a very clear horizontal crack. Okay, so that was what I was doing with the professor. So also, since the UAV is flying in the air, sometimes it's very difficult to identify its own position, which means the vehicle could be taking the pictures from any random angle. So if you try to stitch those pictures together, where those pictures could be taken from different angles, you may have a resultant pictures on the top, and you will see a distortion of the view. And we were working together to correct the positional error, directional error, so we can have proper stitch. Okay, so anyway, this is something that I did related to civil engineering, just to share with you, and I hope students from civil engineering could be interested about this presentation. Now, let me move on to my previous experience about chemical engineering. So, way back in okay, my computer is going crazy now. I don't know why. Way back in 2008, so long time ago. This is the first time that I think the first time I gave an oral presentation in an international conference. I think this was the first presentation that I made. So in chemical engineering, there's a kind of process called chemical vapor deposition. It's a semiconductor process. So what's happening in CVD was it could be utilized for many different applications, such as, like I said, semiconductor, or some coating technologies, okay, or thin film technologies. So the phenomenon inside CVD were those are different kinds of CVD reactors. Usually, you will have a plate called susceptor. So your workpiece stay on top of the susceptor, and you will have some reactants coming from the inlet of the chamber. And usually you will heat up the susceptor. So when the reactant has contact with the susceptor, there will be chemical reaction happening. And due to that chemical reaction, some species or some materials will be deposited on top of the workpiece. So that's why it's called chemical vapor deposition. And there were many different kinds of chamber design, like this is so-called a pancake reactor, because the shape looks like a pancake. And this is a vertical reactor, okay? I didn't have, okay, anyway, I can show this. So, chemistry. From the inlet, you have silane and hydrogen coming from the top, and at the bottom, you have heat. So, silane will become silicon and being deposited on top of the bottom surface. So usually this is very common in semiconductor. You have silicon wafer, you want to deposit layers of silicons on top of silicons. So CVD is one of the way to grow silicon on top of silicon wafer. Okay, so I was working on a topic like this, and I was simulating how it looks like. So let me show you how simulation works, because maybe not every one of you could be learning how to do simulations. So there were numerical softwares that could estimate what's happening inside the chamber. So this is a so-called a streamline of flows. In fluid dynamics, you will learn about streamlines. Or in thermodynamics, you may be learning something about like a flow or streamlines. So whoever is in the field of mechanical engineering, civil, material science, actually all of you probably needs to take thermodynamics, if I'm right. So there could be terminologies like this in the future for you guys. And especially for mechanical engineering, definitely you need to know something about fluid. And streamlines represent the pathway of liquid fluidic particles. So if there's a small liquid particle on the top, it's going to flow through that line. And what's going on top of the cover? This kind of plot shows information in a different dimension. So over here, there's a map representing some physical factor. Here, this plot is showing the velocity of the particles. So red color represents high velocity, blue color represents almost zero velocity. So from here, you not only can see how the particle flows, and also how fast the particle flows. So from here, you can see particles tend to slow down right here, and being really fast right here. Okay, and this is simulation tools help us to understand what's going on inside the chamber. And this is another plot indicating the temperature distribution. And because we are heating up the bottom, so at the very bottom layer, it's very hot. And the temperature tends to drop when it's reaching up here. The reason why the temperature drops so much right here is because there's a flow on the top. The flow carries the heat and then dump the heat at the outlet. Okay? So in this entire chamber, since this is the position where that is having the highest temperature, so chemical reaction is going to happen at the bottom only. Okay? And in my research, I was studying how this distribution is gonna look like. There's going to be a profile, and it won't be flat. So I was doing optimization to make this deposition as flat as possible. Okay, so that was my experience about chemical engineering. Okay, so next I would like to talk about something related to material science. But unfortunately, this presentation was made in Chinese. So I will just show you pictures and then tell you more about what we did. So this is a soft gripper made by 3D printing. We use a kind of soft material to print out a gripper like this because it's soft. So there's an air chamber inside. When you blow pressure air inside the chamber, this chamber will expand. The expansion will cause deformation. So this device will perform a gripping motion. But for robots, this is for robotics research. So we are trying to make soft grippers so that it doesn't break like a tomato. For example, you use a robot to grab a tomato. You don't want to squish it. So you want this grasping to be strong enough, but not damaging the fruit. If you consider tomato as a fruit, some say it's vegetable. But anyway, we need sensing at the fingertip. So we were making sensors like this. This is a very unique sensor. It's made of graphene and some polymer called PVDF. I'm not from the chemical engineering nor the material science. I only know the name of the polymer, which is called PVDF. Whoever is from material science or chemical engineering may be able to understand more or quicker than me. However, I can tell you more about PVDF. It's a kind of material that has piezoelectric effect inside. If the if the molecules inside this material is being aligned in a proper way. So usually for this kind of material, you need to polarize it. Usually for polymers, the molecules inside, they are oriented randomly. But researchers found PVDF could have piezoelectric effect when those molecules are aligned properly. So there's a way to make the molecules align properly is to apply electrical field onto the material. So when you apply electrical field on the material, you have positive and negative. The molecules tend to orient in the same direction. Once you have that same orientation of the molecule, PVDF will have piezoelectricity. But what does piezoelectricity mean? It means if you press it, if you deform it, it generates electricity. So this device, this black stuff, inside this, there's piezoelectric effect, 压电. When you press it, it generates electricity. So piezoelectricity. So if you press it, it will generate a current. The current goes through the cable that we made. We use a device to collect the current. And the system, the computer will recognize, hey, there's a current. So that means you have contact at the sensor. So it could be utilized as a pressure sensor. Okay? So these are cool designs made by my students. So this is what the soft gripper look like from the inside. Inside this area, it's all hollow, it's empty. So if you blow air, because this material is soft, it will expand and it will perform this gripping motion. Okay, and over here she creates some kind of standard testing platform to study the sensor signal. So I would like to show you how this whole thing works. This is like a basic structure of what she did. You have an air compressor right here. You have a pressure valve. And you have controllers to control the valve. You have computers to give commands to the controller. So pressure can be applied to the gripper as you schedule, as you plan. Okay? So everything will be controlled by this computer. And let me see. Okay, so we had many different designs in the past. We have white ones, we have black ones. I don't know why they tend to use different colors. But anyway, my student made different designs in the past. And this is the assembly. So very cool assembly view for you to visualize everything in once. Okay, and let me see. Okay, I think this is more related to material science. Although it's in Chinese, but I can explain to you from step to another step. So my students prepare a solution with a mixture of PVDF and graphene. Graphene is carbon. Carbon formed in a very unique way, and they are usually in a flat structure. So when you place graphene inside PVDF, the graphene will form layer structures inside material. And because of those layer structure, the molecules inside PVDF tend to follow the same orientation in order to have piezoelectricity. So once you have this solution, you apply to a coating machine. And then when it cures, it becomes a flat sheet. It's like a piece of black paper, very black because of graphene. And you can cut it into small pieces. Then we use copper tape and signal wires to hook up the sensor. So whenever this small membrane deforms, it actually generates current, and the signal will be collected. In order to protect this device, because this is very, very thin, and you can easily break it, so we prepare some kind of a coating to protect it. So the material that we use is called PDMS. It's a polymer that is widely used in research directions, such as biomedical applications or some microfabrication applications. So usually for PDMS, there are two solutions. We call the A solution and B solution. You put them together in a ratio of 10 to 1. So then you mix them well, and you need to debubble it. Once you debubble it inside vacuum, you can then pour into a mold and put your device right there. Once the PDMS cure, you have good protection. So how it looks like at the end is like this. Okay, so the transparent stuff is PDMS, the black stuff is PVDF and graphene. This is copper tape, this is white. Okay? Let me see if there's a video at the end. She should have videos. No, it's not a video. Okay, I thought she has videos. So anyway, that's another research that we have done in the field of material science. So to the end of my introductions today, the basic idea I want to share with you is that nowadays research directions are very multidisciplinary. Okay, so you cannot just focus on one subject. You need to look around. And don't be afraid of a subject. So one last story about myself. When I was an undergraduate student, the subject I hate the most was thermodynamics. Okay, and when I studied for my master program, I told myself, okay, I finally can get rid of thermodynamics. So I then focus on manufacturing. So at the time, they told me, okay, it's okay you work on manufacturing, but you need to take required courses in every division. And the one course that I need to take for the thermal division was thermodynamics. So thermodynamics was still there. I still need to pass through the course. I got B plus. I got B plus, which was the worst score I got in graduate program. I got all A, the thermal B plus. Yes. I'm not trying to show off. I'm just trying to tell you how much I hate thermodynamics. Okay. And then, okay, B plus equals to pass. Then I told myself, finally, no more thermodynamics for my life. And unfortunately, when I applied for PhD, due to several different reasons, I need to work with two professors. One is the person I really want to work with. He's in the field of optimization. The other person is our chairman. He's in the field of thermodynamics. If I don't accept this kind of co-advising system, I cannot continue as a PhD student. I have to go back to Taiwan. So I have to accept it. And then I realized, okay, if I continue to be afraid of thermodynamics, I will be doomed by the subject. So at the moment I decided thermodynamics is gonna be in my life eventually. So don't be afraid of it. Maybe if you make friends with it, it will bother you less. But if you become an enemy of it, it bothers you all the time. Okay? So once I have a change of my mind, I realized I'm no longer afraid of thermodynamics, and I got my PhD degree in the title of optimization of a thermal system. So I properly integrate optimization and thermodynamics in my PhD degree. I thought that would be the end of my journey of thermodynamics, but I was wrong. I started to find a job, a professor job in Taiwan. I started to send out applications. All rejected. I only got one offer. The offer was assistant professor in the thermal division in Zhongyuan Christian University. I need to take it or not, or no job. So I have to fake my identity and pretend I'm a thermodynamics professor in my first job. And I even need to teach thermodynamics. So I feel sorry to those students. I'm not an expert in the subject, but I have to teach the course. But thermodynamics helped me to get my first job. What a interesting journey of my life. And eventually the people realized, hey, Ho-Ting, you're not in the thermal field, you are in robotics. Go back to your robotics. So finally, I no longer need to focus on thermodynamics. I'm a robotics professor right now. But because of those journeys in the past, I was able to know a lot of knowledge in different fields, and that really helped me a lot. And I hope this message could be sent to you, and you will keep that in mind. And in the future, if you are afraid of one subject, don't be like that. Treat it as something that could be helping you in the future. Okay? So that's the end of my presentation today. Anything you guys would like to say? Otherwise, we're going to finish today. Okay? Let me get back to the QR codes. If you haven't done that, you can.